So there are these fundamental forces, and the strong and weak nuclear forces we don't notice much in our everyday life because they only are felt over tiny, tiny scales. Basically, fractions of a distance across a single proton or a neutron. That's how close you need to get before you actually feel these forces. But the nuclear forces are so strong. And so if you can build a bomb that kind of plays around with releasing energy from these nuclear forces, you can build something very powerful indeed.
That's the voice of Michelle Thaler, scientist and astronomer at NASA Goddard Space Flight Center. She's today's guest on Press the Button, a Plowshares Fund podcast dedicated to nuclear policy and national security. But first, here are your co-hosts, Joe Cirincione and Michelle Thaler.
Welcome back to Press the Button. Thanks for being with us today for our 60th episode. We have a science episode this week with one of America's leading astronomers, Dr. Michelle Thaler from NASA. She'll help us understand the science of nuclear explosions, and if you wait until the end of her interview, she will explain where gold comes from. We only recently discovered this, actually, and I promise you it's fascinating. But first, we'd like to say a few words about the events of this weekend. Representative Jamie Raskin told us a few weeks ago that the pandemic had exposed holes in our social contract. Communities of color have been hit much harder by the coronavirus because of the underlying social inequities. This is also true when it comes to social justice. In the past few weeks, we've seen African Americans killed while jogging, killed while sleeping in their bed, and now killed when a police officer knelt on his neck for 9 minutes as 3 other officers watched and did nothing. David Rothkopf told us a few weeks ago that we were dealing with a triple crisis, a pandemic, an economic collapse, and a corrupt and incompetent president who seeks to divide us. Sadly, we now have to add a fourth crisis around the issues of the profound wealth inequities in our society and the deepening racial divide.
And racism is a crisis that has been with us for far longer than the other three. We need a change. We need to reorient our budgets, reorient our priorities, root out these systemic biases so that the wealth of this nation benefits all its citizens and that its laws protect all its citizens. As we heard this weekend, no justice, no peace.
You know, Michelle, for me, what this drives home is the need to reorient our priorities, to reorient our budgets. We talk a lot on this show about moving money away from an unnecessarily large military budget at the Pentagon and moving it towards the real needs that our society has. This weekend has brought home just how much work we have to do at home, how much more we need to do for our citizens here rather than engaging in endless wars abroad and ever-growing military budgets.
And how much we have to do together.
Yeah. Let's go back to our show. We begin with a special early warning segment devoted to nuclear testing.
We recently learned senior officials within the Trump administration have considered ordering a U.S. nuclear test. This is huge.
Yeah, we haven't tested since 1992. No country in the world has tested in this century except North Korea. If the U.S. starts testing again, it's going to set off a chain reaction. India, Pakistan, maybe China, certainly North Korea. It is a catastrophically stupid idea. I'm glad you explored it today, Michelle.
I totally agree, Joe, which is why we spent an extra 3 minutes to make sure that we could give this topic the justice it needed.
Thank you, Michelle. And the interview today, as I said, is with Dr. Michelle Thaler. She's the Assistant Director of Science at NASA's Goddard Space Flight Center. She's an astrophysicist and a friend of mine. I met her at the wonderful Conference on World Affairs that's held every year, except this year, in Boulder, Colorado. Her specialty is working on breaking down the dense scientific issues that they deal with at NASA and finding ways to communicate it to the public. You may have seen her on the Science Channel, on How the Universe Works, that show. She also hosts the podcast Orbital Path, which is available through public radio. As I say, we end our interview talking about gold, but most of it's focused on hydrogen and uranium, the science of nuclear explosions. Michelle was just fabulous. I learned a lot. Like, why do we need neutrons anyway? And I think you will too.
After the interview, you'll hear another installment of In the Silo about gender discrimination in the nuclear policy field, what it looks like and what people are doing about it. You'll get to hear from the research team at New America about how you can get involved. But before we get into the episode, we have a final special announcement to share with you.
That's right. I'm retiring. That's not the announcement. You know that already. I've been talking about it off and on for months. But the special announcement we have for you that we're releasing on the Plowshares Fund website and through our emails is that we've selected my replacement. And I'm delighted to say that it's Dr. Emma Belcher. Emma is the lead for the nuclear program at the John D. and Catherine T. MacArthur Foundation. She's been there for almost a decade. She has served in the Australian government. She's Australian originally. She's one of the leading experts in the field, knows the field well. I'm delighted that she's going to be taking the helm of Plowshares. She will take over on September 1st.
And we just could not be more excited. Joe, we're going to miss you. There's no replacing you, but we're really looking forward to Emma's new leadership.
I couldn't be happier about Emma. I really do think she's the perfect president to lead Plowshares into the next decade and beyond, and to reinvigorate and recharge Plowshares and adapt it to the new moment. You'll be hearing a lot more about her in the weeks to come.
Including, you and her will both be speaking at our virtual Chain Reaction Gala on Monday, June 8th.
That's right. This year at Chain Reaction, which is our annual gala, I'll be making my last speech as Plowshares president, and Emma her very first. We usually charge for this event. It's usually an in-person event, but this year, like most other things, it's virtual. It's free and open to the entire public. Go to our website, plowshares.org, to register, and you can hear Speaker Nancy Pelosi, former Secretary of Defense Bill Perry, Michael Douglas, Governor Jerry Brown, Rachel Bronson, and a team from the Science Advisory Board of the Bulletin of Atomic Scientists putting all these crises together for you, and many more. Monday, June 8th, 5 p.m. Pacific Time, 8 p.m. Eastern Time. Go to the website, register, and we'll see you next week.
As always, remember to subscribe to the podcast and give us a rating through whichever platform you're listening to today. We've got a lot for you, and the clock is ticking.
And now, early warning, early warning, early warning, early warning. A 7-minute synopsis of this week's nuclear news.
Thanks, Del. Today's early warning is different from our usual 7-minute segment, given the subject. We'll be spending 10 minutes talking about nuclear testing. As you might have heard, recently the Washington Post broke the story that senior officials within the Trump administration have considered resuming nuclear testing. Now, the United States has not tested a nuclear weapon since 1992, so this would be huge. Joining me today to discuss this are Tom Kulina, Policy Director here at Plowshares Fund, Lily Adams, an independent consultant with the Union of Concerned Scientists who specializes in nuclear weapons outreach and policy issues. Lily is also the recipient of a grant from the Plowshares Fund Women's Initiative for a project to build connections with nuclear frontline communities. And James Acton, co-director of the Nuclear Policy Program at the Carnegie Endowment for International Peace. Lily, Tom, James, welcome to the show.
Thanks for having us.
Thank you so much.
So, James, our time starts now, and I want to start with you. Why would the Trump administration want a nuclear test?
Well, good morning, Michelle. Based on the reporting that we've seen coming out over the last few weeks, the Trump administration, or at least some members of the administration, believe that conducting a nuclear test would be a good way of putting pressure on China in particular to start playing ball on things like nuclear arms control. I think this is a hugely mistaken line of reasoning. I think this kind of testing would be much more likely to fuel a nuclear arms race than it would be to create the conditions to dampen it. But I think it's worth pointing out initially, this is actually a sea change in the reasons for talking about US nuclear testing. Until last week or whenever this report came out, the argument about nuclear testing has always been in terms of, if hypothetically there was some kind of technical problem with a US nuclear weapon, and the only way that we could resolve this question were by conducting a nuclear test, should we do so? It was a debate about whether in extremis one should conduct a nuclear test to ensure the viability of the US nuclear arsenal. It was an extremely hypothetical debate focused on technical issues. It was never a good idea to do it even under those circumstances, but it was framed about the viability of the arsenal. This motivation of conducting a nuclear test essentially to try to coerce other countries is an idea that stems from, we're right back now here into the 1950s, the 1960s. So this is a kind of sea change in the potential reasons for conducting a nuclear test.
How quickly could the U.S. conduct such a test? Could it happen before the election?
There's two issues to think about here. One is what kind of test they're trying to conduct. Part of the reason why testing historically has taken a long time to set up is because the US has tested, as other countries have as well, with huge amounts of instrumentation inside the test hole in order to try to get, it's called diagnostics, but in order to try to learn exactly what happens in those fractions of a second before the explosion from the weapon destroys all this testing equipment. So setting up all this diagnostic equipment, and you're actually talking here about meters and meters of equipment that typically gets lowered into the hole where a nuclear testing takes place. Setting up that equipment could take months, if not years. So there's no way that they could conduct a fully diagnosed test. But given their rationale, this geopolitical rationale, they may not want to do that. So sticking a nuke down a hole and filling it up, I think that in and of itself could probably be done before the election. But I also think you have to take into account, I find it hard to believe there wouldn't be legal challenges. You may get court injunctions. There would be a lot of protesting. So I'd say this, from a purely technical perspective, if all they want to do is explode a nuke in a hole, my guess is you probably could do it before the election. When you take into account the legal and political challenges, I think it's touch and go whether or not you could actually accomplish it by then.
Tom, how do you see this playing out in U.S. politics?
Thanks, Michelle. Well, I think it's important to step back and look at the big picture here, which is this is part of the Trump administration trying to tear down the entire bipartisan security agreement system that has reduced nuclear threats for the past 50 years. So we've seen, a withdrawal from the INF Treaty, Open Skies Treaty, the Iran nuclear deal. The administration is now trying to slow roll the New START extension and now take on nuclear testing and possibly get out of the Comprehensive Test Ban Treaty. So if you see it in that context, I think it helps explain what the administration is doing. So they're using this proposal to have a three-way arms control agreement with Russia and China as an excuse not to extend New START, which expires next February. And now they're using the possibility of resuming nuclear testing and therefore undermining the entire nuclear testing, anti-nuclear testing regime, also as an excuse to bring leverage to get China, as James said, into this negotiation. So I think you have to, which, by the way, I don't think they're serious at all about really having a three-way negotiation with China and Russia. So I think I see all of this as a political ploy to keep undermining what I see as a tremendously important set of agreements to reduce nuclear risks to the United States. And quite rightly, what we've seen is Vice President Biden come out very strongly against a resumption of testing for all the reasons we've discussed here. It's not needed for technical reasons. It's not going to bring China to the negotiating table. In fact, it'll probably push them away and give China an excuse if they wanted to resume the nuclear testing. And it's simply not going to make the United States safer in any way.
So I appreciate, looking of how this is going to affect relationships with other nuclear armed states. But Lily, what does this mean for those who live here in the United States who maybe have lived downwind from some of these tests in the past?
I think this consideration is one of the most important reasons for why we should never consider resuming testing, that our previous explosive testing killed and sickened hundreds of thousands of people across the country. This, we've already seen in response to this news, really powerful statements coming out of people who were impacted by test downwind in Utah and Nevada, and members of Congress speaking out against this kind of resumption, because this was incredibly devastating for those communities. And it's also not just Nevada and Utah. The fallout from explosive nuclear weapons tests spread all across the country, and there were extremely high levels of exposure in places like Arizona and Idaho and Colorado and New Mexico and Montana and even Guam. So I think if there was any movement towards actual testing, there would be extreme public outrage. But I think what's also important to remember is that kind of even just the suggestion is really morally appalling because of the impact this has had on people's lives. When I've talked to people who are downwinders, the pain of even hearing their government suggesting putting people's lives at risk again is extreme. It's traumatic, honestly, to consider doing this again, even if we're talking about underground tests, although those themselves can have a lot of really severe environmental and health impacts. So I think what this says to people who have experienced testing before is that the government has no consideration of their well-being and of the harm that they've done to these communities in the past, which is really painful to hear from your government.
In our final 2 minutes, I'm curious to hear from the three of you. James, you mentioned that there would be legal challenges. Lily, you have mentioned, members of Congress speaking out. What would we likely see if there are more potential trial balloons, that this is something the administration is seriously considering?
I think you will continue to see outrage from the states where people have felt the most severe impacts of this. In the United States, we're just starting to see people speak out, but I think that would only increase. And in the past, public concern over testing of the environmental and health impacts was what led in part to things like the Limited Test Ban Treaty and negotiations around the Comprehensive Test Ban Treaty. So I think we would likely see that again from the public.
Tom, is there anything we could expect from the Hill?
Certainly there'll be a lot of opposition coming, particularly from Democrats on the Hill, although Republicans should be concerned as well. I think the key question is, as James was discussing, how soon could a test be done? I agree with him that I think a test could be done very soon, within a few months, if the administration was really serious about doing that. And therefore, we can't wait for the next fiscal year to try to bring pressure against this action. But in the next defense bill for the next fiscal year, I think you will see, and we're already seeing, legislation being offered to prohibit any nuclear test in the next fiscal year. And again, I think this will have near unanimous Democratic support to ban any nuclear test in the next fiscal year. It's not clear how much Republican support it will get, but it's also not clear that we have the luxury to wait that long.
James, final 30 seconds go to you.
I think it's a useful analogy here was during the George W. Bush administration, there was an experiment planned called Divine Strike, which was to conduct a very large conventional explosion underground at the Nevada test site. And there was such intense opposition to this, particularly from Utah, about fears of radioactive dust being kicked up from the ground by the conventional explosion. The opposition was so intense that the George W. Bush administration was forced to back down on that issue. I was trying to be funny without joking on Twitter, actually, when this all first came out, that, conducting a nuclear test is pretty much the best way of testing whether there are any circumstances under which a Republican presidential candidate could lose Utah. And I think that's why this won't happen. There's a chance it will happen, and that's very worrying. But ultimately, I think the politics of this are going to be so terrible that if this is seriously pursued, the administration probably won't succeed. But hopefully they won't even seriously try to do it.
And with that, our time is up. Thank you so much for joining.
Thanks, Michelle.
Thanks, Michelle.
I'm Joe Cirincione, and it's my pleasure to be talking with Michelle Thaler today. She's an astronomer at the Goddard Space Center here in Maryland. Michelle, thank you so much for joining us.
Hey, great to be here. Nice to see you.
Well, we're going to talk about fission and fusion and the elemental forces of nature and the energies that produce the nuclear explosions and why nuclear weapons are different from all other weapons. And you are the perfect person to talk about this. In fact, you're known as a person who can explain complex scientific matters in a way that's understandable to people. It's led to a very long career that you've had on the Discovery Channel, on the Science Channel. Can you tell us a little bit about yourself and how you got here?
Well, sure. I mean, I think it's funny, people often don't know the benefits of their own failures in life. I loved science from when I was a very small kid. I mean, my mom said that by the time I could walk, I was trying to go out and look at the stars. And I was one of those students that didn't do particularly well in my science and math classes because the way it was explained didn't make any sense to me. And the way that science was taught separate from math and everything just was sort of all by itself. And then I realized there was this wonderful story that everything fits together in. And so I'm one of these people that didn't do well. I got C's and even a couple D's in my science classes in college. But it turned out that I loved the science, but I couldn't piece together what the story was. And then in the end, what that turned into was that once I kind of got it, it's like, okay, after 3 times trying to pass quantum mechanics, this is how it works. Really, it's not that complicated. And so I think that I just was a person that looked at science as more of a story. And that's how I learned all the math. And eventually I got a doctorate in physics and I got a job with NASA. And I've been with NASA now for, I would have started in 1998. So it's 22 years.
And what do you do for NASA and at Goddard?
Well, I started out at NASA as a postdoctoral research fellow. I was at Caltech at the Jet Propulsion Laboratory, and I started out as just kind of a pure research astrophysicist. I was writing scientific papers, I was doing observations. I started working on a space mission called the Spitzer Space Telescope, which was kind of like Hubble, but it was all infrared, all heat light. And during that time, the Spitzer mission needed somebody. NASA headquarters asked them to come up with a whole education plan, a whole communications formal plan. Communications at NASA had been done, sort of more at NASA headquarters or by the astronaut program. And now at this point in the 90s, NASA wanted, a space mission to have a good communication plan. And so like a lot of people do, they said, well, give it to the postdoc, let's have Michelle do it. And turns out that managing $1 million a year communication budget is a full-time job. I had to learn a lot of new communities, a lot of new ways to reach out, a lot of new strategies. I wasn't a communications major. And but having learned all that, I found out I really enjoyed it. And so now I'm a communications scientist at NASA. I still stay as active as I can in what the scientific discoveries are. But then my job is to try to communicate it.
Well, we are now in the 75th year of the nuclear age. It began in the deserts of New Mexico with the Trinity test, the first atomic bomb invented by U.S., British, and Canadian scientists at the Los Alamos Manhattan Project. And we moved rapidly from fission devices to A-bombs, atomic bombs, by the early 50s into thermonuclear devices, hydrogen bombs, H-bombs. The H-bomb uses fusion. the atomic bombs use fission. A lot of us understand the history. I've written books on the history of the nuclear age, but it's much more difficult to understand the science and to appreciate what it means that human beings are able to manipulate the elemental forces of nature, that we're able to tap into one of the core energies in the universe. Can you help us understand this? Why are nuclear weapons different from all other weapons? What is the energy that is being released in these processes of fusion and fission?
Well, let's take us back 75 years ago when I think people were realizing just how destructive these things could be. I mean, they must have just been wowed. I'm going to try not to use a lot of jargon, but the one thing that we talk about in physics and chemistry is something called an electron volt. And an electron volt is kind of, you can think of it as the energy released when an electron makes a bond or is released from a bond. This is how chemistry works. For chemical reactions, we're talking things like combustion, burning. A lot of times we were making bombs out of things that were meant to ignite, like gunpowder. Okay, so a gunpowder is a chemical reaction. Things are combusting, they're combining with oxygen. And that means that electrons are kind of switching around between one atom and another and binding atoms together. But all the action is in the electrons. And when you have sort of an electron bond breaking or forming, and atoms get stuck together or they get pulled apart, you have things that are in the vicinity of a couple electron volts of energy. That's sort of the amount of energy that's released. And this is where numbers very soon get almost kind of stupidly large. So to give you an example, some of the first nuclear devices, they were talking about kilotons, 20 kilotons, the equivalent of that much TNT. So basically 20,000 tons of TNT. When you think about that in terms of electron volts, this is kind of crazy. The first nuclear devices had about 10 to the 32 electron volts. That means a 1 with 32 zeros. Now let's think about that. So we go from reactions where each single reaction has a couple electron volts to one where each single reaction has 1 with 32 zeros after it. And that's how much was released in that one particular bomb. And of course, so the amount of energy released in nuclear reactions is so much stronger than the amount of energy released in chemical reactions. And when people realized that you could make a weapon out of things that were messing with the nuclear process itself, the nucleus of an atom, not the electrons going around, but the actual nucleus in the middle. And so I thought we'd have a conversation about why. Why is it that so much more energy is released? So what do you know about the fundamental forces of nature?
Wait a minute. I asked the questions here. What do I know? What do I know about the...
Yeah. So, okay, there's a force right now that you and I are taking advantage of right now because we're sitting down and gravity is holding us down here on the Earth. We're not flying off into space. Gravity is one of the fundamental forces of nature. And if you've ever taken a fall, even just like fallen on a slippery sidewalk, the amount of acceleration you feel as you hit the Earth, gravity doesn't seem all that weak. It seems like a pretty strong force. It keeps the sun in orbit, the Earth in orbit around the sun. It keeps us on the surface of the Earth. But let's talk about how strong other forces of nature are compared to gravity. Let's say gravity is our one unit of force. So the next force that people are familiar with is something called the electromagnetic force. And this is the attraction of two charges. Positive and negative charges attract. Different charges attract. And this force is much, much stronger than gravity. And you should realize that, because although gravity is holding me down in my chair, what gravity really wants to do is accelerate everything to the very center of the Earth. Gravity is pulling us all into the very center of the Earth. And that's not happening because this chair is holding me up. The electrons are repelling each other. There's electrons in my body and electrons in the chair. And as they get close to each other, that force repels, and I don't just fall through the chair, all the way into the surface of the Earth. So if gravity has a force of 1, that's our force unit, electromagnetic force is 10 to the 36 times stronger. So a 1 with 36 zeros. That's a lot stronger than gravity. And that's why we don't just all collapse into the center of the Earth. The electromagnetic force holds us up and holds us together. The repulsion between electrons. Now, there are two other forces that we don't really think of much in our lives, although they're actually responsible for us existing, and those are the strong and weak nuclear forces. And the strong force is named because it is a very strong force. So if gravity is 1, and this strong force would be 10 to the 38, one with 38 zeros. And a strong force then is about 100 times stronger than electromagnetic forces. So if you think about two electrons trying to repel each other because they have similar negative charges, strong force is 100 times stronger than electric repulsion. So, and then there's also this thing called the weak force, which we're going to talk about a little bit in an atom. That's a little bit weaker than the strong force. That's if gravity is 1, the weak force is about 10 to the 25, or 1 with 25 zeros stronger than gravity. So there are these fundamental forces, and the strong and weak nuclear forces we don't notice much in our everyday life because they only are felt over tiny, tiny scales. Basically, fractions of a distance across a single proton or a neutron. That's how close you need to get before you actually feel these forces. So those are the fundamental forces. But the nuclear forces are so strong. And so if you can build a bomb that kind of plays around with releasing energy from these nuclear forces, you can build something very powerful indeed.
Yes. So we started out with fission. We started out with splitting the atom, which is something scientists discovered in the late 30s. So this is very old, knowledge that we've acquired recently in the human species, but almost 85 years ago, we discovered fission, and that was splitting the atom, and that releases a certain kind of energy. And then we used the discovery of that energy, what gave us the atomic bomb, to develop the fusion bombs, which is the bringing of atoms together. Now, we're talking here about the strong force in both cases. Can you help us understand this? And you could start whichever one you'd like, fission or fusion.
So, I mean, one of my sort of naive questions as a kid was how come you get energy from both splitting atoms apart and putting them together? How can you get energy? Right? So it's like I take an atom and I rip it apart and you get energy. I take an atom and I put it together and I get energy. And so this all has to do with this thing called the strong force. And we can talk a bit. I mean, this is where I just love this stuff about how the nucleus of an atom really works. Yes. And why do you need protons and neutrons? We're going to talk about both of those things. Now, the nucleus of an atom, I think most people know, is made up of protons and neutrons. Those are sort of the basic particles. And electrons they tend to orbit farther away from the nucleus. And at very high temperatures, when things get hot, you may have heard the term something is ionized. What does that mean? It means it gets so hot the electrons just fly away. The electrons get so much energy, they're no longer bound to the nucleus. Because the reason the electrons hang around at all, and this is where chemical reactions come in, is that there's an attraction with the electromagnetic force. The protons are positive, and they usually attract a similar number of negative charged electrons. So that's all electromagnetic. But if you give everything a lot of energy, the electrons fly away, and you're just left with the protons and neutrons. And that's really, when we say something is an atom, we say it's a hydrogen atom or a calcium atom or an oxygen atom. Really what you're talking about is the number of protons. The number of protons define what sort of chemical element it is. So, that you can have different numbers of neutrons, and that's the word that we call isotope. So you can have the same number of protons, but different numbers of neutrons in an atom. It's still, like, for example, you can have different carbon. There's carbon 14, there's carbon 12. There's different, in that case, it's just a different number of neutrons, the same number of protons. Anyway, so let's talk about, how you get energy out of both putting atoms together and also breaking them apart. And this has to do with the strong force. So one of the things you may have wondered is, let's start with fusion, because in some ways it's actually kind of easier. And as an astronomer, this is what I study because this is what powers stars. And so in the case of the sun is mostly made of hydrogen, which is the very simplest chemical element. In essence, a single proton. A single proton, that you could call that a hydrogen nucleus. And protons and neutrons both have this strong force. So one of the things that you're going to figure out is how nuclei glue themselves together. So helium, it has two protons that are bound together. And you would ask yourself, okay, protons are both positively charged, so they want to fly apart if they don't like being together. But if they get close enough to each other, if there happens to be two hydrogens and they're moving around and they end up kind of coming close to each other, if they get close enough, that strong force will kick in. Mm-hmm. And that strong force is more than 100 times, like we said, stronger than the repulsion. So all you need to do is get them close enough, and that strong force will bind them. into another atom. And of course, when you think about temperature, the way that physicists describe this is they use a word called kinetic energy, which means how fast things are moving. The temperature really is how fast atoms or molecules are moving around. And if they're going fast, you can get them to ram close enough to each other to get this strong force to stick together. So strong force is the sticky force. And neutrons also have strong force, but they don't have any charge. So if you have neutrons around, that'll help the atomic nucleus stick together even better for the most part. And so neutrons will create more strong force, but they don't bring any electric charge for repulsion. So they're a nice kind of atomic glue.
Can I pause you right there? I did not know that. I really did not understand the role of neutrons in keeping the nucleus together. Thank you very much. Perfect. I've learned something already. Thank you.
That's right. And then this is going to come into a discussion when we talk about fission, because with fission, you have these big nuclei. I mean, uranium, right? Uranium has 92 protons. Yeah. That's a lot of protons. And the protons are all trying to repel each other electrically. And the nucleus is so big in that case that the strong force is getting kind of weak over the scale of the nucleus. They can't really feel each other's strong force. But you put lots of neutrons in there, and the neutrons help glue it together.
When the scientists assembled at Los Alamos to begin the Manhattan Project in early April 1943, they were met by one of the chief physicists there, Robert Serber. And he had put together a mimeograph sheet of papers that they called the Los Alamos Primer. And he gets right to the point. He's trying to explain to the scientists what they're doing here. And he says this: the object of the project is to produce a practical military weapon in the form of a bomb in which the energy is released by a fast neutron chain reaction in one or more of the materials known to show nuclear fission. Well, we now know that that's uranium. Tell us what's going on there.
That's right, the fission reaction. Okay, so I guess for the idea is that let's talk about this strong force. So, what's going to happen is that the uranium atom is very, very close to not being stable. It really wants to break apart because the strong force can only be felt over tiny little scales. And so now the nucleus itself has gotten so big that it really can't hold together very well. And so it's basically just waiting for some input of energy, and it's going to break into smaller things. And I guess in the case of uranium, it usually breaks into krypton and barium.
Yeah.
And so it breaks into those two things. And so what's going to happen is that when you disturb the nucleus at all, it's going to want to go unstable. And that's this fission reaction. And in fact, one of the things that I didn't know, I learned this in physics class, that there are some uranium deposits, naturally occurring uranium deposits, that give off lots of heat because some of the uranium is naturally fissioning at any moment. I mean, it's just right on the hair edge of wanting to go. I want to bring up something called binding energy, because this is going to explain where the energy really comes from. Now, the thing that kind of, as a kid, blew my mind about how the sun works. The sun takes these protons and it rams them together hard enough that they actually form helium nuclei. At the end of the reaction, you end up with a helium nucleus that has 2 protons and 2 neutrons. And one of the things you'll learn as you go through this whole thing is that protons can turn into neutrons. So they can actually, you get protons and neutrons. They're not really elementary particles. They can actually turn into each other. But you end up with something at the end that actually, if you add up the mass of the particles, should have more mass than what you began at the beginning. So a neutron actually has slightly more mass than a proton. So an atomic nucleus with 2 protons and 2 neutrons should have more mass than where you started. And as you know, the whole thing about how you get energy out of a nuclear reaction is Einstein's famous equation, E equals mc squared. Mass can be converted into energy. So E equals mc squared, E equals energy. That's the energy you get out of it. M is the mass converted, the amount of mass converted to energy. And C is the speed of light, and that's a big number, right? So the speed of light, I mean, in terms that humans like Americans understand, it's 186,000 miles per second. So you take that number and you square it, multiply it by itself, and you get a huge number. So the idea is that if you can convert a little bit of mass into energy, you get this giant explosion, and that's what nuclear weapons are based on. So the thing about nuclear reactions, both fission and fusion, is that you're actually looking at different binding energies. With a fission reaction, you have a very large nucleus, like uranium. and it's barely holding together. It's so big that strong force can't hold it together very well. Instead, what happens is if you input a little bit of energy and disturb the nucleus, in the case of like an extra neutron, all of a sudden the nucleus splits apart, and the two nuclei that are left over are much more tightly bound. They can feel that strong force much better. So each of those two smaller nuclei now are relaxed into this lower energy state, the different binding energy state. So for small atoms like hydrogen, you actually get energy out by fusing them together. And as you fuse more and more of these particles together, the strong force is able to really get it packed together, and it releases energy by relaxing. And for very big atoms, you have to get the energy by breaking the atoms apart and create smaller atoms that are more tightly bound together than these big atoms. And we can actually talk about this in astrophysics, the perfect atom that's exactly in between those two processes. So you get energy out of fusing small ones, and then you get energy out of breaking up bigger ones. The one that's right in the middle is iron. And we can talk a bit about what iron does. But anyway, let's talk about how much energy is released in these explosions. So for the Hiroshima bomb, we had, you said, about 100 pounds of uranium. And the uranium was allowed to break up into these smaller atoms. The amount of mass that was converted into pure energy was about half a dime's worth of mass. So if you think about, a dime coin, break it in two, that's about how much matter disappeared and was converted into pure energy. And for a very strong hydrogen bomb, a much more powerful bomb, about 2 kilograms is converted into pure energy during that reaction. So, hydrogen bombs are many, many, many times stronger. In the case of Hiroshima, you were dealing with things that were in kilotons of TNT, thousands of tons. And for hydrogen bombs, you're dealing with many megatons, millions of tons of TNT. So, hydrogen bombs are on the order of 1,000 times stronger than fission bombs, than uranium bombs. So the sun, by the way, just in case you want to know, the sun converts about 4 billion kilograms of mass into energy every second. So 4 billion kilograms is the size of a pretty decent mountain, I'd say. So that much mass is converted into pure energy inside the sun every second.
So what we're doing with the hydrogen bomb is literally reproducing the processes of the sun here on Earth. It's like taking a little piece of the sun and having it be on Earth for that microsecond. And we're getting a taste of that, a taste of the sun's energy. This is the fundamental sort of energy source in the universe, the fusion that goes on in the sun. And we know how to replicate that now. I mean, that was
a tiny fraction of a second. This is the destructive thing. You expose, in a hydrogen bomb, you expose a population, to a tiny fraction of a second of what it's like to be in the core of the sun. And you get intense destruction in that case.
I want to ask you two more questions, one profound and one just really, really interesting. It's amazing to me that human beings understand this and are able to manipulate matter and energy at these fundamental levels. How do you think we're doing with this knowledge?
There's so many things right now going on. As you know, I'm a pretty optimistic person. I love things. It's hard to really understand why we use all of this knowledge for such destructive purposes. As a scientist at NASA, we have, more than 30 different Earth science satellites that are all describing what's happening to our planet right now in terms of how fast the climate is changing and what we're doing to the planet. We have that knowledge, and we don't seem to be doing anything good with that knowledge, at least not yet. The thing that is worrying me most is our planet is so changing so quickly right now because of warming, that we're going to be looking at a huge amount of geopolitical change in the next 100 years. This is actually a prediction from the scientists at NASA. This is nothing that's an outlier. These are our conservative scientists. We're now looking at probably the ocean level rising by about 3 feet by the year 2100 in about 80 years. And it doesn't sound like a whole lot, but there are a lot of areas of the world that are low-lying or close to the coast. And this could potentially cause 1 billion people to have to move. They'll either become refugees and have nowhere to go, or we'll have to find places for these people to go. And in the past, whenever we've had such a disruptive event, it causes wars. And then this is my big fear. So we have this event coming up that's going to change the way our borders are. There's no way around it. And we have all these people sitting on nuclear weapons. And, if we say to, say Bangladesh, it's like, well, we don't care. Bangladesh is, a meteor, 3 feet sea level rise will get rid of most of Bangladesh. There'll be hundreds of millions of people trying to move into India and China. And then India and China will say, well, who's going to help us with this? And will this kick off a big confrontation?
Yeah,
I see that coming. And then that's what I'm really worried about.
Okay. At the beginning of the show, I promised our listeners that if they stayed around for the end of the interview, you would explain where gold comes from. And I don't mean from gold mines. And this is a new discovery, and I heard you explain it, and it was just fascinating. Can you please tell us, where does gold come from?
Well, so, we were talking about this nuclear fusion process, and you noticed that we said that iron was the perfect atom. That basically iron's binding energy is such that if you try to fuse iron together or if you try to break it up, nothing happens. Everything's already in a perfect binding state. And so stars are able to fuse hydrogen into heavier and heavier elements. They keep adding protons, fusion keeps going. For most stars, even pretty massive stars, bigger than the sun, you get to the element iron. And you try to fuse iron, you don't get energy out of it. So what happens is that the core of the star has been doing this nuclear fusion reaction. It tries to fuse iron together, but it doesn't get any energy out. And all of a sudden, that nuclear reaction collapses. You've got this giant star with nothing to support it, no reaction in the middle to explode it. And so the star goes unstable. And this is something that, in star life's terms, things take millions or billions of years. This happens in a fraction of a second. As soon as the core of the star starts to try to fuse iron, boom, the star explodes. And that's called a supernova explosion. And we've observed these. We actually observed more than about 20 of these a night with our telescopes around the world. So 20 solar systems exploding violently every night. So that generates most of the chemical elements that we're made of. But the really heavy ones, they have things like gold and silver, platinum, uranium, all of those things, the things that are big nuclei. Honestly, we never really saw these coming out much from supernova explosions. We saw a lot of carbon and oxygen, all the stuff that we're made of. But, the heavier stuff was not made in very great abundance. And so we were wondering if something else had to happen. So what we observed recently with the Hubble Space Telescope and several other observatories around the world was we observed something, they're called two neutron stars. And a neutron star is what's left over when a star tries to fuse iron and explodes. The core collapses because there's no longer any explosion, any nuclear reaction to hold up the core. And so basically you end up with these giant balls of neutrons. They're about 10 miles across, and they are literally atomic nuclei. They have the density of atomic nuclei. A teaspoonful of this material would have about as much mass as Mount Everest. They're balls about 10 miles across. We observed thousands of these. And recently we observed two of them where there had been a binary star, two stars that were orbiting around each other. Both stars died and exploded. And now there were these two little balls of neutrons, these 10-mile balls, and they spiraled in together. And because you had two giant atomic nuclei come together, that fused all of these bigger atoms that we've never seen before. So things like gold and silver and platinum and uranium. So as far as we know, the only thing that makes gold, so here's my wedding ring, right? The only thing that makes gold in the universe is these two corpses of dead stars, these two neutron balls colliding together. In that one explosion, we saw 10,000 times the mass of Earth in gold produced. And in a matter of seconds. And you ask yourself, how often do we see one of these events? We see them about once a day. In the universe, our telescopes pick this up about once a day. It's called a gamma ray burst. And if you just look at the amount of gold produced in one of them that we were finally able to observe, that gives us as much gold as we need in the universe. In the moment those two neutrons came together, they produced as much energy as the rest of the observable universe combined. In the entire sky, we can observe trillions of galaxies. Each galaxy has hundreds of billions of stars. in that 1 second of coming together, that single explosion that created atoms in your wedding ring,
Wow.
that actually outshone the rest of the universe. Yeah.
So my wedding ring came from a neutron star collision.
Yes. And so did the bismuth. So did Pepto-Bismol, by the way, made of bismuth. I mean, all kinds of things, but not just the gold.
You just ruined it for me. Pepto-Bismol. It was such a romantic notion. I think I might see if I can cut it right at the wedding ring. But thank you very much. Well, Michelle, thank you so much for taking the time. I know you're busy talking and filming. And can you tell us a little bit about where people can find you, where they can follow you for more scientific explanations?
Well, sure. So, I mean, I do help host some of the television shows on the Science Channel. There's one called How the Universe Works, and there's one called, I think it's called Space's Deepest Secrets. And, they get a great deal out of us NASA people, because I'm not paid to be on those shows. I'm a NASA employee. They come and interview us, they make a show out of them. But I'm glad the science is getting out. So you can definitely find me there. For a while, I did a podcast for NPR called Orbital Path. So I think there's like 3 seasons of that you can find for free if you search on Orbital Path NPR, and and I'm around at NASA, so come on by.
Well, great. Well, I'm retiring soon as president of Plowshares, and I'd love to be your agent because you are a remarkable talent. So thank you very much for sharing some of the scientific knowledge with us. It was the clearest explanation I've ever heard of where the energy in atomic and hydrogen bombs come from. Thank you very much, Michelle.
Thank you, Joe.
For this episode, we go back in the silo, where Plowshares Fund Senior Program Officer Cara Wagner sheds light on a groundbreaking report called The Consensual Straitjacket, 4 decades of women in nuclear security.
Most people making the decisions around nuclear weapons have been men. And that's obviously a problem due to the fact that half of the population are women.
When I went to work at the Pickering nuclear power plant, and I was one of the first nuclear energy workers there, life was very difficult. The plant was not built ever expecting women to work there.
We have too many still all-male panels, too many articles that quote only male experts, too many women leaving the field, not making tenure, not rising in leadership.
We still haven't really had our Me Too moment in the national security community.
You just heard the voices of several women leaders in the national security and nuclear policy field. Beatrice Finn, Rumina Velshi, Laura Holgate, and Heather Halbert. They're part of a growing movement to change the conversation around nuclear weapons and to ensure the voices of women are actually being heard at the negotiating table.
A lot of our findings actually have to do with this idea that there's this kind of male-dominated nuclear priesthood that really is at the core of a lot of the nuclear decision-making. But one of my favorite things about this project is that it reflects on how diversity is important, not only in terms of representation, but also because bringing different voices into the room, people with different perspectives, could lead to actual better policy making, better processes, and better outcomes.
That was Dr. Alex Stark, a senior researcher at New America, one of Washington's leading think tanks. Stark was a co-author of New America's groundbreaking report. It's called The Consensual Straitjacket, 4 Decades of Women in Nuclear Security. The study, supported by the Plowshares Fund Women's Initiative, includes interviews with 23 women who have worked at senior levels in the national security field. Here's co-author Elizabeth Weingarten on the provocative title.
People across the nuclear field were preventing themselves from really innovating, incorporating diverse or different lines of thought, advancing policy solutions and ideas, and that the effect was something like a straitjacket. It didn't seem like many people in the field, except for the people who were being kind of marginalized and left out, were terribly upset about that.
Rich with analysis and practical research, the report explores the gender dynamics surrounding hierarchy, language, and ideology, and how women working in these fields responded personally and professionally. And it struck a chord. The Consensual Straitjacket was downloaded more than 10,000 times, a record for New America. Here's co-author Elena Soros on what stood out to her when conducting the interviews.
I remember talking to women who had kids or had coworkers who had started families, and the expectation just being that they weren't coming back. Having conversations with bosses saying things like, well, you're going to leave after you have the baby, right? Being put in the position of having to answer really inappropriate questions. Those are stories that really stuck with me.
Heather Halbert, a director at New America and co-author of the report, emphasized the ubiquitous experience of harassment that women face in the nuclear policy field.
The incidence of sexual harassment and assault was depressing, but not surprising. The depth of strategies and how women had deliberately made choices about everything from what jobs they took to when and whether they started families, to who they dated, to what they wore, to the words they used, all of that was not surprising to me, having come up through this field. We still haven't really had our Me Too moment in the national security community. There are a lot of people with a lot of stories and a lot of bad memories and a lot of sort of quiet, hey, watch out for this person. But we haven't yet had the real demonstration that we can't go back to business as usual.
Plasher's Fund is dedicated to including and elevating women in the nuclear policy field and transforming it to achieve gender equality. Reports like the Consensual Straitjacket help us achieve just that. For Press the Button, I'm Cara Wagner.
To download a copy of New America's Consensual Straitjacket report, and for details about a current essay contest that the think tank is hosting for reshaping U.S. security policy in the COVID era, visit newamerica.org. Thanks for listening to Press the Button. This podcast is produced by Delphine Vigil, Zach Brown, Derek Zender, Alex Spire, and Will Lowry. Sound design by Derek Zender. Audio engineering by Derek Zender and Will Lowry. Research by Alex Spire. Our theme song is by Lyrics Born and the Poets of Rhythm, sampled with kind permission. Additional music by San Francisco-based bands 17 Evergreen and the Society of Rockets. To continue the dialogue and support our work, visit plowshares.org.